seems right. Exponential growth and decay. Brought into integrals and derivatives somehow. To get started on this, we need a new type of way to attack equations, and it's called separable differential equations. I think it's one of the easiest methods around in this level of calculus. It's one of the easiest things I'll show you is how to separate an equation. And there's lots of equations out there that are separable, and I'll show you what I mean by that in just a second. A differential equation of the form dy dx equals f at y, g at x is called separable. What we mean is when we take the derivative, we have a very specific y function and a very specific x function on the other side. We can break them apart somehow. I'm going to give you an example right away. So if you're like, what do you mean break it apart? I'm going to do that in just a second. And we can separate those variables by bringing the f at y over here with the dy, the dx over here with the g at x, and then we can solve really complicated equations, shockingly complicated equations, with only one little move. It's just one little move that's going to make that happen. And I'll show you what I mean. The solution is found by anti-differentiating each side with respect to its thusly isolated variable. What are they talking about? Here, let me show you. It's really, really nice. Complete on a separate page. We're already onto a separate page, which I think I have all ready to go here. The first one, solve for y if dy dx equals xy all squared. Let me just tell you how difficult this situation is. To actually do the antiderivative of this, the way it sits right there, like that's dy dx, and we want to undo that derivative and do antiderivative, when there's x's and y's over there, we have nothing, no tools whatsoever to handle that situation when the dy dx has y's in the answer. And I need to tell you, we've been protecting you from tough equations. There's no reason why the dy dx shouldn't have x's and y's in there when we get to real world applications, like real world type situations. But let me just show you some algebra that takes this problem and really breaks it apart. And I almost said separated it. And that's really what I'm going to do, is I'm going to separate this thing. So I'm going to write dy dx, oops, don't get my pen going yet, dy dx. You know what? It's that time of year. Easter's coming up. It's time for Easter purple. Dy dx equals x squared y squared. Now I've only done one thing on that line to attack this thing, but it's already much better. See, I put it into separable form. X squared, y squared. Now the x terms are all in one piece. The y terms are all in one piece. And that allows me to do this move. Watch what's coming next. And to be honest, that's the whole method right there. Everything that comes next is very nice. So you got to look at that for a second and make sure that it's clear what I did there. Let's talk about dy, dx, x squared, and y squared, what I did with all those things. We found out before that dy and dx, actually, that's just delta y and delta x. It's y2 minus y1 and x2 minus x1. It's a piece now. And so I can move it around as I would any fraction. That's the advantage of Leibniz notation. So what I did is I brought the dx from the denominator over here and brought it up over here. And now it looks like we're used to with integrals, dx. And then I looked at this and said, well, x squared can stay over there with dx. I'm okay with that. But this y squared's got to move over here, and I made it 1 over y squared. That's the separable part. The dy dx is separable. Now, if the equation's separable, I can get this, which at first glance you might be unimpressed, but now I'm going to do one more thing. I'm going to just take the integral of both sides. And life is wonderful. That's ordering pizza time. When you get a separable equation to that moment, the rest is pretty straightforward if we've laid the good foundation from last chapter. And that was the, see how this side's dy and that side's dx. That was the part where they said the thusly isolated variable is that over here's only dy's, over here's only dx's. So finding the integral of something with y is dy, and finding the integral of something with x is dx, apparently we're pretty good at that. Now, as it turns out, we're not very good at it at all. We can do really simple ones. But a lot of the game after this is about getting better at doing tougher integrals. But for now, these ones are we can handle these. Let me tidy the one up on the left a little bit to get ready for it. Y to the negative 2 dy. And this one's integral of x squared dx. So y to the negative 2 dy is, so I guess it used to be y to the negative 1 before it took its derivative. And then so there's a negative in there. Negative times what's in front. Okay, I guess I need a negative here. I'm going to leave space there, okay? Because here come the c's. Now, yesterday I warned you about the c's. And they're going to really come to roost here. Integral of x squared dx, that's 1/3 x cubed. Okay, that one I think by this point you might have sort of memorized. When that one just pops out, you don't have to think, oh, what do I do with the 3? It just pops out. But get ready, always be ready to go, well, sometimes I got to play with the coefficients. We're in pretty good shape here, except for one big idea. These integrals didn't have limits on them. They're just talking about doing antiderivatives, essentially. These were indefinite integrals. We didn't know the limits of summation. If we did, life would be good right here. But we don't, so on each one of these, I need a c. Now there's a c over here, which I'm going to call c1. And there's a c over here, which I'm going to call c2. There's a constant that pulls out of each of those. Now if you're ahead of me on the c's, you're like, well, it doesn't really matter where I put the c, because if that c over there is a 10, and this one over here is a 5, I can put them together and make a new c, -5. And that's absolutely true. There's not a really big problem with the c's. So don't let the fact that I start writing c1s and c2s and c3s freak you out. I'm just sort of keeping track, because in a minute I'm going to do some substitution, and I got to know which c I'm going after, basically. And there will be some choices here, but I've got to know which c is which. So what I'm going to do is just a little bit of work on this. I'm going to just tidy it up a little bit and change it to -1 over y equals 1/3 x cubed plus c3. That's going to be my first version of this answer. Can you see it's well on its way? They want to know solve for y, and I'm well on my way for solving for y. There's some problems with solving for y. One is this is 1 over y. Another one, there's a negative out there. Not a big deal. And then there's a constant I don't know. Now, if they didn't give me more information, I'd be stuck with this, a family of curves that gives the right answer. But they did better than that. Sub in x equals 1, y equals 1. And the facts are you can sub that x equals 1 and y equals 1 in just about anywhere you want, at any time you want. You can isolate here better and make a new constant and do that. I don't know. I think the first time I learned this, the C1, C2, C3s all confused me. So the first chance I got, I subbed in to get the C. I didn't wait any longer to get the C because maybe I was confused about the whole thing. You might isolate y first and make a new C and carry your C around and do that if you want. But that is just part of the art of math here. So I'm going to sub this in here. I get -1 over 1 equals 1/3 plus this C3 that I've got. That C3 was just, lots of textbooks will have a little thing over here. This C3 is just C2 minus C1. Whatever those constants were, this is the new constant when those two things were subtracted. Again, some books make a big deal out of this, others don't. So I get -1 equals 1/3 plus C. I get -4/3 equals the C. So therefore I have -1 over y equals 1/3 x cubed, but now I know the C. I know this C. I know C3 is -4/3. I don't really know what C1 or C2 are, and actually as it turns out, I don't even really care what C1 and C2 are. I was trying to solve for y, so if this was a 7 and this was a 8 1/3, and that's how they worked out to -4/3, I don't really care, and that's what I was trying to get at yesterday, is that I'm not really too worried about anything but one of the C's. At some point, I got to get one of these C's nailed down. Now, the reason I left it like that and didn't isolate the y to begin with is I want to talk about this situation. We've acted all the way along like every equation out there can be solved down to y equals. And that's not really true. Sometimes an equation you can't isolate y just like that. And I'll just put a motivating one in red up here. Let's say I had an equation where the relationship was y squared plus y equals x squared, something like that. Solving for an equation that says y equals, we call it implicitly, explicitly, is not easy to do here. Really, really difficult. So we start to let go and we go, okay, well, if it's going to be difficult, we'll just leave it in implicit form. So we solve for y when we can. And if it's just got y's in the equation, then we live with that too. So we're starting to grow a little bit in our willingness to define equations. But this isn't too bad. I can get y by itself here. Back to purple, and I can fix this up. First of all, I'm going to go 1 over y equals negative 1/3 x cubed plus 4/3. I hope that's not too crazy. What I've done there, I've just multiplied the whole thing through by negative 1. And now different people have different methods how to handle this. I just go, well, you can do anything you want to both sides. So here what I'm going to do is flip both sides. So this side becomes y, and this side becomes 1 over negative 1/3 x cubed plus 4/3. Which isn't bad, but we certainly like to tidy these things up if we can. I'm just going to multiply top and bottom by, I'm going to choose negative 3 here. And so this is negative 3 over x cubed minus 4. I'm just going to check that because I did that all in my head. Multiply the top by negative 3, I get negative 3. Multiply the bottom by negative 3, I get x cubed minus 4. This was actually a reasonably simple answer to a pretty complicated mess of equation. Yes? Checking the answer? Ooh, that would have some times to it. You'd have to do dy dx, get it in terms of x, and then have your expression for x and for y and sub all that back in, square it, and see if you get the same thing. That's got some torque to it, the whole thing, So you have to have a little faith that you've done everything right here. Okay. However, without losing sight of what we've accomplished here, most of the work of the new work was right there in the separation of it. The rest of it, I just took integrals of both sides, did some isolation, and found that C. So don't get sidetracked by my discussions about C. I'm just mentioning all that stuff, so when it comes up, you're ready for it. Any questions about that one? More time? Was there a second one I had to do before I move on? Yeah? When we talk about triggers, and the notes sort of try and give you the trigger for whether something's separable or not. And when you're doing the homework that has separable in it, you sort of have a hint there. But the real challenge in moving into tests and exams is to go, which method am I supposed to use here? And the trigger for separable is that you can see a group of y stuff and a group of x stuff that can be pulled apart. See, this is this is a complicated. Let's give this thing proper respect. This is a complicated differential equation. Y prime is 6x squared over 2y plus cos y. There's a lot going on there. However, the trigger for us is that this might be a separable equation, is that when I look at dy dx, the numerator of this thing is 6x squared, the denominator is 2y plus cos y, and breaking this into an x function in the numerator and a y function in the denominator makes my life workable because I can do some separation here. And here's the separation. And that's the order of pizza line there. If you can break these things into a y function multiplied by dy and an x function multiplied by dx, you're in the home stretch. The rest of it is just pretty simple integration and maybe some subbing. It depends on the question whether you have to do subbing or not, whether you're going to stick with your family of equations or not. Okay, so next step. Now that I've got them separated, take the integral of both sides. So I got integral 2y plus cos y. Now it doesn't look as intimidating as it does before. That's a pretty simple integral. That could have been on the test a few minutes ago. Yeah, that's no problem. And certainly this one, no big deal as well. And I'm going to make an omission here. And we're going to talk about my omission. All right? Let's see. Integral of y squared is, 2y is y squared. See, that one is in my brain. Yeah, I don't have to think about that one. 2y, y squared, bump. There's no playing around with that. Cos y is sine y. Okay, careful. Cos and sine, it's easy to get the signs reversed. No pun intended. I just go, derivative sine is cos. Yeah, okay, check those ones. Over here, 2x cubed, I think, is going to do the job. And let's just talk about these c's for a minute. I might have overcomplicated the c's in the previous example. There should be a c over here. The c that pops out of that integral. There should be a c over there. The one that pops out of there. But I could just move that c over and put it with this c and say, oh, I'll make a new c, which is that c, subtract that c. So you can get a little bit forward thinking here and just go, okay, well, I know there's c's out there, and that's the big C. That's the combination of this C and that C. And when the time comes, I'll just solve for that C. Would we ever need to know the individual C's? Not that I can think of right now. That there's no time when knowing the individual C's out of the brackets is going to matter. So life is good. I'm done. Now, do you see the major problem here? Isolating y is virtually impossible here. I can't come up with an explicit equation for y that we've been used to getting because it's got a y squared and a sine y. There's no way to isolate with those. There's no way to factor them or complete the square. There's no tricks I can do to do that. So that's the best I can do. Solve the differential equation. There's the differential equation right there. And so now we just need to grow up a little bit that we might get equations that cannot be expressed explicitly for y. That y is in there and the x's are in there. You give me an x and y, I can sub in, I can solve, I can do whatever, but it's not y equals anymore. I'll just move this down here. Find this solution to this equation that satisfies this initial condition, though. And I'm going to add a word there. Often this is called the particular solution. Apparently there's lots of curves that have this as their derivative, and we want to find the particular one that has when x equals 1, the y is equal to pi. We want that specific solution. This is going to allow us to solve for this c that I've put out here. So I just sub that stuff in. So I get pi squared plus sine pi equals 2 times 1 cubed plus c. Pi squared I can't do anything about. Sine of pi, though, ding, 0. And then that's a 2, so that's minus 2. So the c is pi squared minus 2, and so therefore y squared plus sine y equal to 2x cubed plus pi squared minus 2 is our particular solution. Is there any questions about that? More time? More time? Yeah. Incidentally, you chemistry, biology people who have been finding the physics examples annoying in calculus up till now. It's often physics we lean on. Now we're coming full circle now. This is very chemistry, biology oriented, what we're headed towards here. Still more time? We're good? Oh yeah, no, back to the PowerPoint now. Yes? Okay, so is it clear what separable means now? It means that the x's and the y's can be pulled apart, even though there are x's and y's in the differential equation. They're grouped together, so you can break them apart and do what I did here. And this is just describing what I did. I divided by the f at y, and then I put the g at x with the dx there. Okay, law of exponential change. Okay, I'm going to talk about exponential stuff, and you already know exponential stuff, but I'm going to give you just a slightly different view on exponential stuff that will help us to access some different equations. Recall that when we studied exponential growth and decay in the past, we often used the equations of the form y equals a b to the x. That is, there was some growth factor, and this in the brackets could be a 2 or a 3 or 1.07 or whatever it was, and then some initial amount. The A was always the initial amount. Notice that the rate of change is proportional to the amount present. I'll go to this in just a second. The reason that things like coronavirus and rabbits are so dangerous is that the growth rate is proportional to the amount that's there. That is, once you get twice as much of it out there, the next generation is that much bigger again. Let's talk about just rabbits for a second, okay? Let's just say I have a pair of rabbits. And in the spring, they have 5 baby rabbits. And that doesn't seem like a big deal. The population went from 2 to 7. And you're like, okay, now there's 7 rabbits in my backfield. Pretty exciting stuff. The next spring, there's now 4 rabbits that can breed. Maybe 4 females. And they all have 5. You see what happens very quickly? This is exponential growth in 2 steps. In 2 steps, you're like, oh, that's going to be crazy. Now, there's going to be rabbits everywhere. And if you've ever seen some nature videos, and they'll show what happens when a organism or an animal gets into a non-native environment where it doesn't have any predators, the populations can explode. Like just unbelievably amounts of mice and rabbits in a certain area for a while. Usually what happens is the predators notice, and they go, oh, hundreds of rabbits, and then the wolves automatically start having more kids. They just know somehow life is good. Instead of, individual wolf babies, you get litters of 3 and 4 because they're like, game on. Yeah, there's lots of bunnies out there. Here we go. So there's this. It's all tied together. Why bacteria again is so dangerous is that the more the population, the more bacteria in the dish, the more you increase. When you only have 5 bacteria, and that's an unrealistic number for bacteria, but just to give you an idea, when there's only 5 bacteria and the number doubles to 10 bacteria, you're like, oh, okay, no big deal. 10 bacteria was 5 bacteria. That's no big deal. But once there's 100,000 bacteria and that doubles to 200,000 bacteria, things just got out of hand. And the reason that happens is because, for your biology people, is lots of times this is all caused by splitting. So you got 5 bacteria and they split into 10, no big deal. We got 100,000 bacteria and they split, that's an extra 100,000. That's why the growth rate is tied to how many are there. It's proportional to how many you actually have. Radioactive material is like that too. The more radioactive material you have, and there's a sort of a splitting that goes on in radioactive material as well, where things sort of start breaking down. And the more you have to break down, the more breakdown that happens. And so it drops off very quickly when there's more there. Money's like this too. They talk about the rich get richer, and that's the nature of money. That's not the nature of society. That's the nature of money. If you've got $1 million to invest, and your money doubles, you make $1 million. If you got $10 to invest and you double your money, you only get $10. Yeah. So that's why it's all very proportional here. So let's consider the bacteria example in more detail, and this is exactly what I was talking about. Suppose we had a population of 1,000 bacteria at a certain time, and it is growing at a rate of 300 bacteria per hour. If then instead there was another population, somebody else had 2,000 bacteria on their hand somehow, or they picked it up from somewhere, their rate is 600 bacteria per hour. Double as many bacteria means double as much growth. That is, the hourly increase in population is proportional to the amount of bacteria present. That comes to a very simple differential equation for this situation, for exponential growth. The change in population, dy dt, is equal to some constant, depends on what we're talking about and how fast it grows, times how many there actually is right now. And this is the k value that we'll talk about a lot here, it's that proportionality constant. Okay, all that talking to say for exponential growth, dy dt is going to be ky. The amount you grow by is going to be some multiple of how much there actually already is there. And now we've got a differential equation with y's in the answer. Yep. We can solve this differential equation actually pretty easily. It's separable. That's why we had to talk about separable equations first. It's extremely separable. I can bring the y over to this side as 1 over y. I can leave the k over there. take the integral of both sides. Ooh, there's that ln absolute value of y that popped up over there. Let's just talk about that again for a second. Does it have to have absolute value of y? This y didn't specify. It can be positive or negative. So ln has to be prepared for that. So ln has to be prepared for positive and negative answers. And then if I bring the ln over, I get e to the kt plus c. A little bit of algebraic manipulation, and you get this, which is the same exponential equation you saw before. A, b, t. So this is coming at your same exponential equation, but looking at it from a growth standpoint. Question? When you go from 1 over y and do the integral of it, from here on in, you'll have to go ln absolute value of y, unless there's something about the question that tells you, oh, I don't have to worry about that. Sort of reminds you of square root, right? At some point we learned in square root, you've got to go positive and negative square root, always, unless you've got something in the question that tells you that, well, I don't have to worry about the negative square root, okay? So in this one, there's nothing here. It's just a general situation, so there's nothing that can tell me that I can ignore that. And that's why we end up with plus minus down here. Now, we can deal with this by making that plus minus c into just some a value. You say, okay, well, I can start off with a positive number or a negative number there, and then I don't need to incorporate the plus minus there. If you want, put this into a money example. You can start with $1,000, or you can start with negative $1,000. You can put both of those things in there. That makes sense in money. One's savings, one's a loan. You know what I mean? So the positive and negative, don't get too worried about that. The result shows that the only growth function that results in growth proportional to the amount present is the exponential function. That's the important part of all this, is if your growth is proportional to how much is there, you're talking about an exponential function. You don't have to be wondering if there's some other function out there that you could use. And the initial constant is just, that a out front is just, we just use that for when t equals 0. So we usually sometimes called y0 as well. So anyways, after all that, and actually all that stuff is good foundation to understand where it's all coming from. But here's what you really need to know out of all that. If y changes at a rate proportional to its present value, that is, if dy dt equals ky, then you can use this equation, y equals y naught, e to the kt, as your equation for the situation. That's the solution to that equation right there. And you've used that equation before. That's not an unfamiliar equation. This time we're using e as the base. E is a natural base to use because it has a lot of natural properties and all this. So if this k value in the brackets here is positive, whatever we're talking about will be growing. And if that k happens to be negative, then whatever we have will be decaying. Just to mention in all this that you actually can do compound interest with this. You don't have to compound quarterly or semi-annually or monthly, if you remember all those. You could compound continuously. That means you're getting interest on your money every moment. It's worse than that. An infinite number of time periods. And there is a limit to how much interest you can get in these situations. So if you want to use a formula for interest compounded continuously, then that would be the function to use, or that would be the equation to do. So we're familiar with ones where the compounding occurs annually, semi-annually, quarterly, monthly, or at some other discrete interval, but now we have one that we can do as a continuous growth. I feel like examples are looming. Am I right about that? If, however, we let the number of compounding periods per year approach infinity, we will be compounding continuously. Since the rate of change is proportional, then this is the version of the equation that I suggest because it's much simpler. So if you're doing a continuously compounding money situation, this one would be compounded continuously. And the R is the continuous interest rate. So you can use the other one, but the E one is much easier to use. Yeah, when you use the E in the equation. Oh, and here comes a couple of examples. Even as much as I've talked all the way along the way, we're in pretty good shape time-wise, I think. So actually, I'm going to do A over here, which is compounded continuously, and I'm going to do B over here. But I'm actually going to do B first, just to refresh your memory on how this all works. When it's compounded quarterly, we use the compound interest formula. Hopefully you remember at least the formula, maybe not how to use it exactly, but here's my introduction on how to use it. So with the compound interest formula, I first put in the principal, which here the principal was $800. I started with $800. Then I need the interest rate per interest period. It says 6.3% per year, but when you're compounded quarterly, you don't get all that interest in each quarter. You only get a fourth of that. So this is 0.063 over 4. And it's 8 years later, so it's 32 compound periods. Let me just pause there, because that's either like, boom, that comes right back up in your head really quick, and you're like, yeah, I remember all that. Divide the interest by 4, multiply the years by 4, because it's quarterly. Or you're deeply confused and you'll have questions. But I'll type this in, and then you tell me what your questions are about the old compound interest formula for quarterly. And I get 800, 1 plus 0.063 divided by 4. And then exponent here is 32. I get 1319.07. Any questions about the old compound interest formula? Okay, so the new interest formula, when things are compounded continuously, is A equals A naught e to the RT. So in this case, my amount is going to be, yes, my original $800, then multiply by E, and I just put that rate right in the formula, 0.063T. Let's see what I get when I type that in. So you can see why compounding continuously exists. The banks aren't completely worried about continuous interest here. Let's see, where's my E? 0.063. Whoops. I guess I needed a T value there. That was an 8. Wasn't it 8 years? Yeah, 8 years. Times 8. Close the brackets. I get 1324.26. Not overwhelming, the difference between getting your interest every 3 months versus continuously. Enough to matter in financial circles, though, and certainly enough to matter if this was millions of dollars we were talking about instead of thousands of dollars we were talking about. Any questions about that one? More time? More time? No? Let's talk about radioactivity just a little bit. Radioactive substances decay by spontaneously emitting radiation. Basically, we're talking about unstable substances who cast off radiation on the outside and slowly break apart and become less of what they were. This is right tied to carbon dating and how they find out how old things are. These substances have been found experimentally to decay at a rate proportional to the remaining mass. It's all a probability thing. If you got 1,000 grams of something, and some of it decays, less is going to decay for somebody who's got 1,000 than somebody who's got 2,000. Yeah, because it's all about how many of these atoms are going to decay. So the decay of a radioactive elements is the exact same we've been talking about, except it's going to have a negative K in there instead. Y can represent the mass of the sample or the number of radioactive nuclei present. This particular equation works for mass or it works for how many actual atoms you have. Why is the negative sign used here? Just to remind us that we're talking about decay. Yeah, so we switch to a negative sign out there, and we know that K is actually going to be positive because we've taken care of the negative up front. You don't have to do that. That's just a way of managing the positives and negatives. So if Y0 is the number of radioactive nuclei present, or mass at time 0, then the number that is still present later will be, we use this equation, Y equals Y naught e to the negative KT. So that's not really any different than what we saw in the previous examples. Half-life, I believe you've seen, I think it was in advanced functions, but maybe it got glossed over. And the half-life of a radioactive element is the amount of time required for the sample to decay to half of what it was before, or the time required for half of the radioactive nuclei present to decay. It just tells you how long it takes to use up half of what you have. Okay. Example, find the half-life of a radioactive substance with decay equation Y equals 1. Okay, I've got to actually come up with the actual half-life. Okay, so do I have that in my examples here? Find the half-life of a radioactive substance with decay equation. Okay, so here's the decay equation. Apparently I can get my Y, that is how much mass or how many nuclei I have left in a decaying substance, and this applies to anything that is actually decaying, not just radioactive substances. And it says find the half-life. And doesn't give me any other information. Yeah? So here's the important thing about half-life. Half-life is find out how long it takes to have half of what you started with. Initial value of this equation is Y naught. It's that leading coefficient. It tells you how many you're starting with. So at the half-life, we'll have half of whatever it was. Now, so if it was like 1,000, now I got 500. If it was 10,000, now I got 5,000. You just take that initial value and divide it by 2, which doesn't seem all that helpful. But can anyone see the unbelievable amount of help this has? The original question didn't mention any populations. It didn't say how much we had at the start versus how much we have now. And that freaks people out because you're like, how can I do this question if I don't know what it starts with and what it ends with? All I know is it starts off with some value, and I got to get down to half of that value. But great things are about to happen. Because the Y naught cancels. Now, if I got a Y naught over here and a Y naught over there, I can divide everything by that Y naught. So what I get here is 1/2 equals e to the negative KT, and that's definitely the order of the pizza moment in questions like this when you divide that out, because now doing the rest of this solving is pretty straightforward. Now hopefully your E's are up to date and you know what to do next. If not, hey, I'm going to teach this like you haven't really seen it in a while, which might be true. It might be like November since the last time you thought about how do I deal with this. I'm trying to solve for t here. How do I move e to the power of over to the other side? Let's let you think about that for a second, because the big thing there is to, if you don't remember, is to know how important this step is, because without this step, you're helpless here. Ln, yeah, ln is right there going, yeah, I'm exactly designed to deal with exponentials, so I get this. Ln 1/2 equals e to the negative KT. Then I can divide both sides by k and the negative. And while that's a correct answer, it's not as good as we can do. We can improve this situation a little bit. Because 1/2 is 2 to the negative 1. And then using log laws, that negative comes out front, and I actually get this. a pretty handy little equation, actually. Instead of doing all that work every time, it's pretty nice to know that the time it takes for an exponential decay to half its life is just ln 2 divided by whatever that k is. You're like, what if I don't know the k? Well, that's going to be an important deal in all this, is knowing what the growth factor is, or the decay factor for a particular substance. A lot of these type of derivations. That's the good news for you biology, chemistry people. And a lot of times it comes down to this exact move on the exponential equation. You put in something over here and something over there, and then you just ln it out to get your answer. Yeah? So if that's new and weird to you, it's okay. We're going to do a bunch of them. But do you have any questions there? More time here? Back to the PowerPoint. Trying to keep things moving here. Okay, so yeah, that's what I solved for. I solved for ln 2 over k. Yeah. Mallow growth with other bases. Up to this point, we've been using y equals y naught e to the kt. The implication was that e is the superior base. That might not be true, actually. It could be if you got something that's doubling at regular intervals or halving at regular intervals or growing at 5% every year, you may decide that a different base is better. But there's a lot of advantages to using e. So what I would say is use e as your base, unless there's something about the question that forces you out of that. So you could use any base you want. You can use 2 as your base, or if you want to talk about doubling time. You can use 1/2 as your base. You want to talk about half-life. You can use 1.05 as your base if you want to do 5% growth. There's lots of choices for that base there. Now, if y equals y naught e to the kt is written as y equals y naught b to the ht, how are those two things related? Oh, can I do this? Did I put this in my other note here? Oh, yeah, I did. So, and this derivation really isn't necessary, but I want to do it just to establish again how we go about these things. Yeah. And why the exponential equations are with the power of ln in your hand, why the exponential equations are actually pretty repetitive. They're pretty easy to work with. What do you see here? If I want to, somebody wrote their equation using e to the kt, and so they had this equation for it, and I want to make a new equation, y equals y naught b to the ht. I want to use a different base with a different growth factor, yeah, with a different number in there. What's blaring at you? Well, I hope I've laid the foundation for what's blaring at you in these situations that happens. I'm going to get my red out. What happens again and again in these type of situations is that y naught just goes. And that makes the rest of it doable. Let me rewrite that next line. So I've got e to the kt equals b to the ht. And I'm going to take ln of both sides. Ln's always involved. Yeah? As soon as there's e in an equation, you're like, let me just write down ln. I just know that's coming in the middle of this. Here I took ln of both sides, so this side just becomes kt, and this side becomes ht ln b, and I'm going to hesitate there again, because I really want you to see the big deal of everything that's happened there. Ln and e cancel out. I can use log laws on the other side now, and my hint is I'm going to switch over to my red pen. What do you see? K over here. No K's over there. T over here. HT ln B. The T's go now. And so I get a nice relationship between the K value, if you're going to use the E as your base, and the H and B if you're going to use B as your base. So it's a nice transformation over. Do you do all these steps every time? Well, that depends. You get to know them, really, is what happens. You get to know how you switch over from one base to another. What was the main idea there? The main idea was, in exponential equations, there's often some cancellation, and often ln can help you out. So you have those two weapons available to you when you're dealing with exponential equations. Let me just say it one more time to be clear what we're trying to accomplish there. If one person tries to do a particular question using e as the base, they might have a particular k value. Someone else decides they want to use a different base for the question. This is the relationship between the variables involved. They want to choose a different base. That's no problem. They take this k and they solve for their b value. So you just, or for their h value for their equation. So you can easily transform from one version of this to the other. I'm going to do some examples coming up where you'll get a taste for what that looks like. Oh, yeah, here, this exploration, right back to the exploration, which will give you a feel, start to give you a feel for what all these letters are that are flying around here. Choosing a convenient base, and I'm going to make this full size. I hope that's going to leave me enough space, but I want to be able to read this. A certain population Y is growing at a continuous rate, so the population doubles every 5 years. So they've done some study. Let's just imagine this is some town. Maybe it's the town in the WandaVision show, and they've noticed that, hey, every 5 years this population is doubling. Maybe this is the population of rabbits. Maybe this is the number of coronavirus cases, whatever you're talking about. But some population doubles every 5 years. When you look at that, and the first time you stare at it, you go, well, there's two choices for the base here. Doubling every 5 years tells me that wouldn't 2 be a good base because we're multiplying by 2? And then meanwhile, you're like, well, Mr. Todd was really on about E. Shouldn't I be using E? Yeah? And the answer to the question is no, whichever one. One might turn into be a little bit easier than the other, and I say a little bit easier, but whatever base strikes your fancy. So number 1 says, let y equals y naught 2 to the ht. Okay, let me just write that down. They're suggesting that if I could use 2 as the base, and that would be my exponential growth. So since y is equal to 2 y naught when t is 5, what is h? Well, this is a perfectly nice equation, but I don't know what h to use in there. But they did tell me this information. When t equals 5, this thing will have doubled. So check this out. When t equals 5, we'll have 2 y naught equals y naught 2 to the 5h. And again, I'm just going to leave that up there again because this happens again and again in exponential type situations. What do you see? Happens all the time. Exponential ones all the time. It's the go-to trick with exponential equations is that that'll just disappear. And so now I've got this 2 equals 2 to the 5h. In many questions you'd have to ln here to track down this 5h, depending on the information they gave you over here. But this one's particularly nice because they both have base 2. So I can go 1 equals 5h. So my base, my h is 1/5. This makes for a particularly convenient version of this equation, which you were supposed to see in other courses along the way. That is, if you've got something that has a doubling factor here, you can use the equation y equals y naught 2 times t over 5. When I write it in that form, does it look a little more familiar? I hope that's come up in biology, chemistry, but it certainly was in the applications in advanced functions. My brain tells me I don't know how much of that we did last year, but basically it says, hey, if you've got some population that doubles every 5 years, multiply by 2. How many times do you multiply by 2? Well, it depends on how many multiples of 5 you have there. So it's actually a simple little version of the doubling equation. What is the relationship h to the doubling period? H is the doubling period. No, is the reciprocal. That is, it was doubling every 5 years, so I went over h in the denominator. Okay? Let's move this up here out of the way and see if I can get another question in here. How long does it take the population to triple? Seems like an impossible question. Seems absolutely impossible. We don't know the initial population. So how could we know when it triples? I do have my equation now, y equals y naught t over 5 for this particular situation, because it doubles every 5 years. So I got a beautiful equation for it. We're going to see through this problem and see how it's actually possible to do this question without knowing the initial population, without knowing the final population. All we know is that the population has tripled. Yeah. Sub in 3 y naught. I don't know what y naught was. I don't know what the initial population is. All I know is it's triple now. So what I get is 3 y naught equals y naught 2 to the t over 5. And it's very intimidating if you haven't done one of these before, because it's like, well, how am I supposed to solve that? What a big mess. And what's the big move here that I've been hammering away on for the last few minutes? Yeah, these go. And where that comes from is, if it was initial population 1,000, and this was 3,000, it would be 3,000 over 1,000, which would be 3. If it was 1 million and 3 million, it would be 3 million over 1 million, which would be 3. It always comes out to a multiplier of 3. We need this multiplier to be 3. Okay, here's the next big weapon in these. And I'll know I'm doing a good job when you're really bored and you're like, okay, so every single one version of these we sub in over there, and then now I got to solve for t. How am I going to get that unknown out of the exponent up there? Ln of both sides. Now, when we first did logs, you could do log of both sides, or you could do log base 2. There's lots of choices there, but ln is the natural one. Most of us just start leaning on ln. We go, okay, you know what? If I'm not sure which base to use, I'll just use ln. So I get ln of 3 equals ln of 2 to the t over 5. Why is that so important? Because log laws allow me to bring that down. And then I can solve for the t. And the reason we leave it in that exact form is there's something more to this somehow. You can sort of see that to see how long it triples, check this out. You got the doubling period, 2 in the bottom because it doubles, and 3 in the top because we're looking for a triple. There's some definite patterns to all this, like really built into all this. So I envy sometimes biology, chemistry people, because their equations are very smooth in these situations. They play out very nicely, and all the information is there. And you can see there's be a lot of shortcuts in here available once you got to know the equations well enough. Yeah. I feel like I'm going to run out of space here. Okay, I bought myself an extra page there. Any questions about 1 or 2 there? I'm going to move on to another new page here. I'm going to shrink this up to try and fit more in because I just need it as a reference now. You've got it in front of you, I hope, so you can look at it there. Number 3 says, or maybe that's too small for me. There, that'll do. Just going to buy myself an extra little bit of space in this page. 3. Let y equals y naught 3 to the ht. Since y equals 3y naught, oh no, hey, new question, sorry. Read carefully. They've changed the game here. They said a certain population y is growing at a continuous rate, so the population triples every 10 years. New question. Okay, so my new equation will be y equals y naught 3 to the ht, because we're using tripling Isn't 3 a good base for tripling? Yeah, I think it is. There's no reason to jump in with ease here. Since y equals 3 naught, when t equals 10, okay, so then here we go. 3 y naught equals y naught. 3 to the h times 10. And do you see what's got to happen here again? It's the same. Yeah? Y naughts cancel. I get 3 equals 3 to the 10h. And I get h equals 1/10. Therefore, y equals y naught 3 to the h, t over 10. Very repetitive. I did that question much faster on purpose. I wanted you to see how fast that can go once you get good at that. And by good at that, there's not a whole lot of skills here. It's plug in your triple, in this case double population, and use lons to solve. And number 5 switches over to a decay type question. So instead of doubling and multiplying by 2 every time, or tripling and multiplying by 3 every time, it switches over and says a certain isotope of sodium has a half-life of 15 hours. I think that's accurate, actually. It's pretty close to a half-life of sodium. It's about 15 hours. That is, half the atoms of Na24 disintegrate into another nuclear form in 15 hours. So what are we going to sub in here then? When t equals 15, A equals half of A naught, half of Y naught, half of A naught. A for amount this time instead of Y for population. Although 5 sort of plays loosey-goosey with the A's and the Y's there, but I hope you get the idea there. And so I get A naught over 2 equals A naught 1/2 to the 15h. The A naughts cancel. I get 1/2 equals 1/2 to the 15h. And again, I get h is 1 over 15. And that's 1 over the half-life. That's what they're trying to get to there, is that half-life goes there. And how long is the amount of radioactive decay? Oh, this is the first good question in a while. So let me just get that equation down, and then I'll pause for you to catch up, and we'll talk about this. That equation actually gets given to you in other courses and other grades. Advanced functions, we just give that to you. A equals A naught 1/2 t over 15. What do I still got to do? Newton's law of cooling? And that's it. And then the L'Hopital. Ooh. It's funny. I get up here, I'm like, be fast. And then I'm like, no, got to explain this. I want them to understand it. Okay, let's talk about number 6. Again, it's another question where it's like, how can I possibly get this? But hopefully we have enough experience now that you're not intimidated by this. How long does it take for the amount of radioactive material to decay to 10% of its original amount? We don't know A naught. We don't know A. We don't know T. How can we possibly do this? What am I going to sub in if I want to know when is it 10% of its original population? Brad. A naught over 10. Yeah, that's right. 1/10 of what it was before. I was thinking of 0.10 A naught, but now I got to think and decide whether I like yours better or not. In this question, I like his better. A naught over 10. Yeah. In general, I think thinking of it as a decimal is going to be more powerful, because if this question said decayed to 17% of its original value, it wouldn't have a nice fraction like that, so you might want to go with the decimal. Okay? So that's what I'm going to go with. I'm going to say, okay, so it's 0.10 A naught equals A naught. And I got to tell you, it doesn't take long in these questions before we just go to 0.5, because it's easier to carry around and perfectly accurate. It's a perfectly accurate version of that. And so I get 0.1 equals 0.5 to the T over 15. Those A naughts cancel again, and then ln can get me the rest of the way. Ln 0.1, T over 15 ln 0.5, 15 ln 0.1 over ln 0.5. I like it. And just to get that as a approximate answer, I'll jam that into my calculator, see what I think of the answer. 0.1 divided by ln 0.5. 49.8. Does that make sense? Let's see. Let me take a look at the question again. 15 hours to go to half of its life. So 50 hours to get down to 10% of what it was. Yeah, okay, that does fit. Yeah, so it's a nice little check. It doesn't exactly check the answer, but it does give me a feel for that I'm on the right track. Any questions there? Tomorrow, Lehapatal 1 and 2, they actually go well together. Why they're in two separate lessons. It makes for a long lesson, but they actually go well together. So we'll do that in the morning. We'll see how you feel. And then maybe I'll reappear at 1:45. I know late in the day sometimes you're like, you may as well just teach because my brain's fuzzed anyway, so I don't know how much more I'm going to get done. You know, so this will wrap it up. I got a chance before lunch. Let's see if I can land this before lunch, giving you period 4 as a work period. It's good? Brain's okay? As good as it gets in quadmesters? Questions here? Although the exponential equation y equals y naught b to the ht satisfies the differential equation dy dt equals ky for any positive b, is only when b equals e that the growth constant appears as the exponent. I'm going to do a couple more examples. No, we're not going to make it. I'm going to have to do Newton's in the last section, because I forgot about these two examples before we got to Newton's law of cooling. Back to here. What are they even talking about? I don't know. Let's get a random question, and I'll try and accomplish it two different ways, but quickly. I got to move pretty quickly on these, okay? This is the last example before Newton's law of cooling. 1 and 2 I got to nail down. Okay, so keep it moving. At the beginning of the summer, the population of a hive of bald-faced hornets. I don't know why we chose bald-faced hornets in the middle of all this, but any population you want to talk about, which are actually wasps, is growth at a rate proportional to the population. Okay, that sentence is important. Growing at a rate proportional to the population. That tells us immediately that we're dealing with an exponential equation. So I can jump ahead and say I'm using y equals y naught e to the kt. It's an exponential growth situation. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. So we set May 1st. We set y naught as 10. And I made May 1st t equals 0. We're going to measure this whole thing from t equals 0, and I'm going to call t equals 0 May the 1st. So anything I do from there, May 1st is going to be t equals 0. So what I get is y equals 10 e to the kt. It's a big problem. I don't know y, I don't know k, I don't know t. But what we really want is the k. So let me just highlight that in there and go, in these questions, if we're going to be able to use this equation, we've got to figure out what the k is. But I can find out the k pretty easily. Sub in t equals, I need another time, not the time for that, how many days? In 30 days. So for time equals 30, my new population is now 50. So I get 50 equals 10 e to the 30k. 5 equals e to the 30k. Ln 5 equals 30k. K equals ln 5 over 30. Sort of a complicated looking k value, but it does give me the power I need to be able to do this question. So, big moment. Big step in all this. I know the equation is start with 10 e to the ln 5 over 30 t. I now know that k value, and I'm going to highlight it up here as well to say all that work with that initial piece of information was to get that k value, so now I've got a perfect equation. By perfect, I mean it relates y to t. And now I can do work. If the growth rate continues along the same model, how many days after May 1st? After May 1st. Oh, I made May 1st t equals 0, so that's okay. Nothing to worry about there. How many days after May 1st will the population reach 100? Sub in y equals 100. 100 equals 10 e to the ln 5 over 30 t. What a mess. And then so I get 10 equals e ln 5, oops, careful, equals e ln 5 over 30 t. Ln both sides, ln 10 equals ln 5 over 30 t, and then 30 ln 10 over ln 5 equals t. I'm going to pause for questions here, because I really don't know what's happening out there. You might be like, yeah, just algebraic steps, I got it. Or you might be like, what are you doing? I have no idea what's happening now. And so we got to narrow down which one of those is. I get 42.9, but I typed that in really quickly, so I want to check that in just a second. 30 ln 10 over ln 5. 30 ln 10 over ln 5, looks really good. Did I type it in right? 30 ln 10 over ln 5, yeah, looks pretty good. Does it make sense? To get to population 100, it took 30 days to get to 50. It took only 13 more days to get up to 100. Yeah, fits with what I was doing. Really, 43 days. And biological processes cannot be trusted. This is all guess, based on how populations grow. A nest of sparrows moves in besides the hornets here. Well, all bets are off, aren't they? Anything can happen once the sparrows show up, right? See my backyard when the wasps are crazy. We get lots of wasps, lots of birds are coming. Yeah, so it's always a trade-off. What do you want to talk about? Which step you want to deal with here? Is it good? I hope that when you get to hear that I laid the foundation in the previous examples, that it's just like, okay, so just move it around and use ln when you get into trouble. Yeah, when the unknown's up in the exponent there. More time here. One more before the break. Yes, scientists who use carbon-14 dating I didn't think I did this question separately. No, I was so confident I didn't even do it. Okay, scientists use carbon-14 dating use 5,700 years for the half-life. Find the age in which 10% of the radioactive model has decayed. Okay, so take a look at this. Here's the half-life version of this. And I developed this earlier. Y equals Y naught. It's a half-life question, so I'm going to use 1/2 there. And I'm going to go T over 5,700. That's the nice version of half-life. When you see half-life appear, maybe E isn't a great choice, because this nice equation, which makes perfect sense to me. How many times do you have to half the population? Whatever T over 5,700 is. If it's 5,700 years, you half it once. It's 11,400 years, you half it twice. And it says, find the age of a sample in which 10% of the nuclei have decayed. 10% has decayed. Now we need clever thinking. What am I going to sub in if 10%'s decayed? Oh, good for you. 0.9 Y naught equals Y naught. And I'm going to 0.5s over here right now. And that's the order of pizza moment. Once you're there, everything else falls into place. The Y naughts cancel. 0.9 equals 0.5 T over 5,700. Law on both sides. And so I get T equals ln 5,700 ln 0.9 over ln 0.5. Did I? 5,700 ln 0.9 over ln 0.5. Better get that as a number to make myself feel good about what I've accomplished. 5,700 ln 0.9 divided by ln 0.5 equals, I get 866 years. Someone tell me why that number makes sense. Why does 866 sort of fit with what we were saying? To get down to 50% of the sample should take 5,700 years, so 866 years makes sense for 10%. We're right on top of carbon dating here, folks. You know, you could right now become an archaeologist and go, I can do the math of archaeology. You give me a bone, and using the carbon-4 dating system, it's very, very similar equations that they use. There might be some adjustment factors for environment, temperature, all those kind of things. Questions there? So we'll do Newton's law of cooling right after the break. It does not take long. It's pretty simple stuff.